Hi. Many important functions are defined as the inverses of other functions. For example, the square root is the inverse of the square. The logarithm is the inverse of the exponential, and so on. Inverses are usually implicitly defined functions. That is, to know what is f minus 1 of y, you have to find the x for which f of x is equal to y. In other words, you have to solve an equation, f of x equal y. And since our ability in solving equation is extremely limited, in general, these type of functions are only implicitly defined. This makes these functions harder to visualize and deal with. For example, how can we verify the continuity of a function defined in this way? Since continuity is a very important property, this question makes a lot of sense. In this video, we talk about this and we try to answer to this question. Now, continuity on intervals is a property that forces some notable consequences. One of these is the following. Assume that we have a function defined on I with the codomain j, such that f is a bijection, so it is invertible. It has an inverse f minus 1, and I and j are both intervals. Now, it turns out that if the function f is continuous, it must be strictly monotonic. It cannot be anything else. This might be intuitively obvious, but to prove this is a bit less straightforward. So let's see the argument quickly. If f is not strictly monotonic, so for example, if f is not strictly increasing, it means that there are 3 points, x, y, z, ordered, such that, for example, f of x is strictly less than f of y, but f of z is strictly less than f of y, so it's not larger. In this figure, you see the situation, x, y, z, and d values. Now, if you see these 3 points and you imagine a function that passed through these 3 points that is continuous also, you can see that something goes wrong because you see that this function is definitely not injective. And this is the goal of what we show here. Because if we take a value between f of y, which is the biggest here, and the biggest between fx and fz, in this case f of x, so I see here, we see that there are 2 points because of the intermediate value property. So the function must take the value c between x and y and also between y and z. So we have 2 points, a and b, where the function takes value c. So in particular, this function is not injective, and this contradicts our assumption. So a bijective and continuous function between intervals is a strictly monotonic function. The converse is also true. Let's say, let f be a function defined on I and with values in j, be such that it is strictly monotonic, surjective. Notice that these two combined say that f is bijective, because the first one in particular implies that f is injective. So from these two, we deduce that f is also invertible, and there is an inverse. And moreover, we assume that the domain and codomain are intervals. Well, in this case, we know that f is continuous. This comes from the theorem of monotonic surjective functions on intervals. And moreover, also the inverse function of f is continuous on its domain, which is in this case the codomain of f. Now, this is a consequence again, of the theorem of continuity of monotonic surjective functions between intervals, because f minus 1 has the same monotonicity of f. If f is increasing, f minus 1 is increasing. If f is decreasing, f minus 1 is decreasing. So f minus 1 is a monotonic function. It is surjective because the codomain is the domain of the function f, and the two domain and codomain for f minus 1, j, and I are intervals. So from this, it follows that the inverse function f is continuous. Now, this theorem applies to the proof of the continuity of the inverses of elementary functions. For example, take the sine. As a function on the real line, real value, this function is not invertible because it is neither injective, for example, sine x is equal to 0 infinitely many times, nor surjective. There is no solution to the equation sine of x equal to 2, for example. However, if we restrict our domain to half period, and conventionally this is from minus pi half, we get a branch of sine, which is now, and with codomain minus 1, 1, we get a function that is now strictly increasing and surjective between intervals. Therefore, the inverse function, which is named the arcsine, is a continuous function on its natural domain, which is the interval minus 1, 1. The same applies for the arccosine. In this case, we take as a domain of definition for the cosine, for the restricted cosine, the interval 0 to pi. Now, on this interval, cosine is strictly decreasing and surjective if the codomain is the interval minus 1, 1. Therefore, the theorem of continuous inverse applies, and it says that the inverse function, which is named the arccosine here, is a continuous function on its natural domain, which is the interval minus 1, 1. Great. Now it's your turn. An important example is the inverse function of the tangent, which is, again, a function not bijective, but that becomes bijective when we restrict the domain to the period minus pi half, pi half. In this case, you can show that the inverse function is well defined and it is continuous. This function is named the arctangent. Similarly, another important function is the hyperbolic sine, which is defined in this way. You can check directly, without using any differential calculus, that this function is strictly increasing on the real line, and it is also surjective as a function from R to R. So it is bijective, invertible, and because of the theorem of continuous inverse, the inverse function of the hyperbolic sine is continuous. In this case, you can actually have a formula for the inverse of the hyperbolic sine, which is provided by this relation. Well, good luck, and may fortune always be with you.